Welcome to Climate Change in the West, an EcoWest.org presentation. EcoWest's mission is to inform and advance conservation in the American West by analyzing, visualizing, and sharing data on environmental trends. This is one of 6 presentations that illustrate key environmental metrics. Libraries for each topic contain additional slides. You can download these materials at EcoWest.org. Here's an overview of the presentation. We begin with a discussion of projected temperature changes, and then discuss what's expected for precipitation. Next, we move on to the expected impacts of climate change, beginning with the water cycle, biodiversity, and wildfires. We then discuss greenhouse gas emissions, and talk about some other forms of air pollution. Here are the key points. The West is already warming faster than many parts of the country, and even higher temperatures are expected in the decades to come. Models predict the Southwest will get drier and the Pacific Northwest will get wetter, but the projections elsewhere are more ambiguous. Changes to the vital winter snowpack and the timing of the spring snowmelt will pose challenges to aquatic species and water managers. Plants and animals are expected to move upslope and toward the North Pole in response to the changing climate, but many barriers stand in the way. Warmer temperatures and a thinner snowpack will continue to make the West wildfire season longer and more destructive. Power plants, transportation, and industry account for the great majority of GHG emissions in the West, where only a few states have significant carbon sinks. The nation has made significant progress in addressing many types of air pollution, but millions of Westerners remain at risk from airborne toxics. Let's begin by examining how temperatures have been changing in the West and elsewhere. This video from NASA's Goddard Institute for Space Studies shows how the planet has been heating up since the 1880s. You can see that the temperature increases are most striking in the Arctic, and things have really heated up in recent years. The average temperature around the globe in 2011 was 0.92 degrees Fahrenheit warmer than the mid-20th century baseline. Let's take a closer look at temperatures in the United States. This map, created using the Nature Conservancy's Climate Wizard tool, shows the average temperature across the lower 48. You can see that the West has some of the hottest and coldest areas, often in close proximity. This measure, average temperature, has its limits. It doesn't, for example, account for the fact that drier places such as deserts often have wild swings in temperature in any given day, with 30 or 40 degrees separating the high and low temperatures, while many coastal areas have much less variability. Looking ahead, it's expected to get much warmer across the nation, but the increases will likely be greatest in the interior West, Midwest, and at higher latitudes. These 3 maps show the average number of days per year when the maximum temperature exceeds 90 degrees Fahrenheit. The top map is for 1961 to 1971. The middle map shows the number of days projected by the 2080s and 2090s under a lower emissions scenario, and the bottom one shows projections for a higher emissions scenario. Much of the southern United States is projected to have more than twice as many days per year above 90 degrees by the end of this century. In urban areas, where most of the West's population resides, temperatures have already been rising. This graphic shows that the average number of hours per summer day in Phoenix that the temperature was above 100 degrees has doubled over the past 50 years. Now, a big part of this is a result of the urban heat island effect, in which buildings, roads, and other human development retain heat in a city. But climate change is also a factor, so the trend toward hotter and hotter days is expected to continue. Now let's shift to precipitation. You can see that west of the 100th meridian, conditions are generally drier, except for the Pacific Northwest and the highest mountains in the region. But what's perhaps most striking about the West is how varied the precipitation is and how spotty the patterns are, largely due to the influence of mountains and the rain shadows they cast. Since the middle of the 20th century, some parts of the West have gotten wetter, others have gotten drier. As with temperature, it's a complex pattern. Looking ahead, this map illustrates what's expected to happen with precipitation under a low emissions scenario. The Southwest and California are expected to get much drier, while the Pacific Northwest is projected to get wetter. Here's what's projected under a higher emissions scenario. Once again, areas at lower latitudes in the Southwest and elsewhere are generally expected to get drier, while areas farther north are projected to get wetter. These maps show projected future changes in precipitation relative to the recent past as simulated by 15 climate models. The simulations are for late in the 21st century under a higher emissions scenario. While projections for precipitation are cloudier than those for temperature, climate models are showing that in the spring, northern areas are likely to get wetter, while southern areas are expected to get drier. There's less certainty where the transition between wetter and drier areas will occur, but the hatched areas indicate where confidence is highest. The previous maps looked at projections for the end of the 21st century, but this map focuses on the period between 2020 and 2039, which isn't that far away. Compared to the 1960s, 70s, and 80s, large portions of the West, especially at lower latitudes, are expected to get drier, while the Pacific Northwest and Northern Rockies are projected to get wetter. Changing precipitation patterns will obviously affect the West's water supply, and many scientists believe that climate change will be most conspicuous in the hydrological cycle. This graphic summarizes how climate change will impact the nation's water supply. The interior West is expected to not only get hotter, but drier and be susceptible to worse droughts. In winter, the higher temperatures will mean less precipitation falling as snow, more as rain, which will have major effects on the region's rivers, many of which are dependent on the melting snowpack. Hotter temperatures mean higher evaporation rates, greater water use, and potentially more conflicts over water. Just in the past few decades, we've already seen a shift from snow to rain throughout much of the country, though in some places in the West it's actually gotten snowier. This map shows trends in winter snow to total precipitation ratios from 1949 to 2005. Red circles indicate less snow, while blue squares indicate more snow. Large circles and squares indicate the most significant trends. The areas south of 37 degrees north latitude were excluded from the analysis because most of that area receives little snowfall. April 1 snowpack, a key indicator of natural water storage available for the warm season, has already been declining throughout the Northwest. In the Cascade Mountains, snowpack declined by an average of 25%, with some areas experiencing up to 60% declines. On the map, decreasing trends are in red and increasing trends are in blue. Changes in the snowpack and precipitation patterns, plus warmer temperatures, have already led to an earlier peak to the spring snowmelt. From Arizona to Alaska, most watersheds shown in this map experienced an earlier date for peak streamflow, as shown by the red circles. Only a few were later, and those are shown in blue. Once you factor in future climate change, the surge of snowmelt that feeds western rivers is expected to come even earlier, in some cases more than a month sooner by the end of the 21st century. This map shows projected changes in snowmelt-driven streams by 2080 to 2099 compared to the 1951 to 1980 baseline, under a higher greenhouse gas emissions scenario. Add it all up, and we're expecting to see pretty significant declines in runoff in much of the West, with steep declines expected in the lower Colorado River Basin. This map shows projected changes in median runoff for 2041 to 2060 relative to the baseline of 1901 to 1970. and it's mapped by water resource region. Colors indicate percentage changes in runoff. Hatched areas indicate greater confidence due to strong agreement among the models. White areas indicate divergence among the model projections. The results are based on emissions in between the lower and higher emissions scenario. A 10 to 20% decline is expected throughout California, the Great Basin, the Upper Colorado River, the Rio Grande, and the Arkansas. Now let's shift to climate change's impact on biodiversity in the West and its incredible array of plants, animals, and ecosystems. Temperature and precipitation play critical roles in determining the distribution of plant communities around the globe. Plant distributions, in turn, determine what types of animals are found in various places. This graphic shows how the climate zones compare for various types of plant communities. Because climate change is expected to affect both temperature and precipitation, major shifts in plant communities are projected in the West and elsewhere. One of the West's most striking aspects is the enormous variation in elevation, temperature, precipitation, and therefore ecosystems that are found in just a small area. The scorching desert of Death Valley, 282 feet below sea level and the lowest point on the continent, is only 85 miles away from the snow-capped peak of Mount Whitney, 14,500 feet above sea level, and the tallest point in the contiguous 48 states. Same goes with precipitation. Look, for example, at Washington, Oregon, and Idaho. The Cascade Mountains are among the wettest areas in the country, but to their east, precipitation is scant, except for the higher elevations of the northern Rockies. The result is an amazing variety of ecosystems, ranging from rainforests to deserts, in a relatively compact area. Because some plants and animals require a warmer, drier climate, while others need cooler, wetter weather, the diversity of species can be tremendous in just one corner of one state. Because climate change will affect future temperatures, precipitation patterns, and other elements of the weather, the mosaic of ecosystems in the West is going to be rearranged. This map shows the current conditions, as well as the results from two climate models. The West currently includes arid lands in the southwestern deserts, conifer forests at higher elevations, and shrubs, woodlands, and grasslands in between. The models not only factor in changing temperatures and precipitation, but also account for increasing levels of carbon dioxide, which promotes plant growth. You can see that in the southwest, a large portion of the arid land deserts are replaced with grasslands, shrubs, and woodlands. In the Great Basin, there's a shift from shrubs to savannas. Let's take a closer look at some specific examples of species that will be impacted by climate change. This series of maps shows average air temperatures in August for the Pacific Northwest. Levels above 70 degrees Fahrenheit can severely stress cold water fish, such as trout, salmon, and steelhead, by raising water temperatures. You can see that major warming is expected in the region over the next few decades. Researchers are already documenting a northward movement of birds and other species in response to warming temperatures. This graphic shows results from an analysis of 40 years of data from the Audubon Society's Christmas bird count. Many species are wintering farther north in response to the changing climate. In some cases, species will be able to fly, swim, crawl, hop, or otherwise move to more suitable habitat. But sometimes there will be insurmountable obstacles. This is a pika, a small rabbit-like creature that lives in alpine boulder fields in western North America. It can die in a matter of hours if exposed to temperatures higher than 78 degrees. The pika faces a challenging future because it can only retreat uphill so far. Eventually, it will run out of mountain. The map on the left shows the currently suitable habitat for the pika, but the map on the right shows what's expected by 2100 if climate change continues. According to this projection, vast areas that are now home to pikas will be too warm to support the species. Signature plants of the West, and the animals that depend on them, will no longer be found in many locations if warming continues. This map shows the current viability of whitebark pine, a critical food source for grizzly bears and other species. The viability index ranges from 0 to 1, with lower values indicating lower suitability, and 1 indicating the species is nearly always present in that climate. Here's what's expected by 2090 if emissions continue to increase. The whitebark pine is gone from the lower 48. Now let's shift to another major impact of climate change, the West's changing wildfire season. Scientists have already found that the warming experienced over the last few decades in the West has led to an increase in wildfire activity. One paper concluded that large wildfire activity increased suddenly and markedly, starting in the mid-1980s, with most of that change due to a warming climate rather than fire suppression. Higher temperatures led to a thinner snowpack that melted earlier in the spring, leading to more flammable conditions in summer. The scientists looked at more than 1,100 large blazes that broke out from 1970 onward. Compared to the 1970 to 1986 period, wildfires in the 1987 to 2003 time frame were 4 times as frequent and burned more than 6 times the acreage. The length of the wildfire season increased an average of 78 days. Looking ahead, climate change is projected to make the West wildfire season even worse. This map shows how various ecoregions are expected to fare if global average temperatures increase by 1 degree Celsius. In many areas, the median annual area burned is projected to increase more than 100%. Climate change is expected to make the Southwest drier, lead to more severe droughts, and cause a thinning of the mountain snowpack that delays the onset of the fire season and supplies the bulk of water in western rivers and reservoirs. Warming temperatures and the lack of deep freezes may be responsible for increased activity by mountain pine beetles and other forest insects. This photo shows dead lodgepole pines near Rocky Mountain National Park in Colorado. Around the globe, forests have been experiencing die-offs that scientists attribute to drought and heat waves, both of which are expected to be on the rise in many parts of the West due to climate change. This map shows the location of dozens of tree mortality episodes that scientists have documented. The different colors represent varying types of drought and temperature anomalies. Here's a close-up of the West. In southwest Colorado, multi-year droughts with high spring and summer temperatures are thought to have caused the cases of tree mortality. Along the Mogollon Rim in Arizona and New Mexico, multi-year droughts with high temperatures were also linked to tree mortality. Insects and other biotic agents often play a major role in forest die-offs. High temperatures or drought conditions can weaken trees and make them more susceptible to infestation by bugs, some of which are native, some of which are exotic. In this map, hollow dots represent die-offs with no connection to biotic agents, and gray dots indicate where no biotic agents were linked to tree mortality. But at least in North America, many of the tree mortality events were connected to bark beetles and other biotic agents. In this close-up of the West, you can see that bark beetles were connected to forest die-offs along the Mogollon Rim in Arizona, while wood borers were an influence in southwest Colorado. In California, other insects were linked to the climate-related mortality events. Now let's talk about what's causing climate change: greenhouse gas emissions. This flowchart, created by the World Resources Institute, shows the sources of greenhouse gases in the U.S. economy and how they are produced. Nearly 1/3 comes from providing electricity and heat to buildings, and more than 1/4 is from transportation, mostly driving. Nationally, 3/4 of GHG emissions come from 3 sectors: electricity generation, transportation, and industrial operations. GHGs have risen steadily since 1990, with the growth slowing in the mid-2000s, partly due to efficiency improvements in transportation and the electricity sector, and partly due to a slowing economy. The western states' source profile is very similar to that of the entire U.S. Here's another view of how the West compares to the U.S. as a whole. The 11 western states are responsible for about 17% of total GHGs. Without California, the western states would be about 10% of nationwide GHGs. Some sources are more prominent in the West, and particularly in California, shown in green. Transportation really stands out as a major source in California. Elsewhere, fugitive emissions from oil and gas drilling are especially prominent in the western states, accounting for 42% of the U.S. total. Because most GHGs come from the combustion of fuels for electricity and transportation, economic activity is highly correlated with emissions. Not surprisingly, California is the largest source of GHGs in the West. Interestingly, California, Oregon, and Washington differ from more inland states in their source profile. Transportation makes up roughly half of all GHGs, whereas for inland areas like Wyoming, Arizona, and Utah, electricity generation is the predominant source. California, while making many efficiency improvements to its electrical grid, is also the largest importer of electricity from out of state. 30% of California's power comes from its northwest and southwest neighbors. Wyoming and Colorado, on the other hand, export power. Some states also have the capacity to absorb significant GHGs into their forests and other potential sinks. This slide illustrates how some states' land use and development policies reduce their overall GHG footprint. Most notable are Oregon, Washington, and Montana, with each state's net emissions reduced by roughly 35, 50, and 90% respectively. While California's land sinks reabsorbed almost as many GHGs as Montana's did, the sheer size of California's footprint muted the reduction to only 10% of statewide GHGs. Finally, let's talk about some other forms of air pollution. This slide summarizes the major air pollutants, their sources, and their health effects. Many of these pollutants stem from fuel combustion. The U.S. continues to make progress on improving its air quality since the Clean Air Act's enactment in 1970. This graph from the EPA's Air Trends website displays how regulations and advancements in technology have led to efficiency improvements, lower emissions, and cleaner air. While the economy, the GDP, has continued to grow, the aggregate emissions from the major criteria pollutants that EPA regulates have shrunk by 60% since 1990. Here's a closer look at national trends by each pollutant since 1990. The greatest progress is seen in sulfur dioxide, a major precursor to acid rain. Sulfur dioxide has diminished largely due to emission scrubbers on power plants and advancements in manufacturing lower sulfur fuels. Progress is less substantial on ozone and fine particulate matter, or PM2.5. A significant challenge with ozone and PM2.5 are their precursors. Put simply, pollutants are either created directly by emission sources like power plants or indirectly when precursor pollutants mix together in the atmosphere and chemically react to form a new pollutant. PM2.5 is emitted during combustion, but it also forms in the atmosphere when volatile organic compounds, nitrogen dioxide, and sulfur dioxide chemically react. Here we only focus on direct emissions, and therefore do not cover ozone. However, ozone's precursor pollutants are discussed. This graphic shows how air quality changed between 1980 and 2010, and between 2000 and 2010. There is no data for particulates in 1980. You can see that all of the major air pollutants have declined in recent decades. Here's a slightly different way of looking at the issue, the emission sources responsible for each of the pollutants. Once again, there have been dramatic improvements in recent decades. Although the nation's air quality is clearly improving, tens of millions of Americans are still exposed to unhealthy air. In total, about 124 million people lived in counties that exceeded one or more federal health standards. This map shows the estimated cancer risk by census tract. In the West, areas around big cities such as Los Angeles, Phoenix, Denver, and Portland have higher rates of cancer associated with toxic air pollutants. This map shows how many days on which a city's air quality index exceeded 100, a level at which pollution can be unhealthy for sensitive groups. Los Angeles stands out as the western city with the worst air pollution, while Seattle and Portland in the Pacific Northwest have relatively few bad air days. In general, the number of bad air days has been decreasing over the past decade. Let's take a look at the sources of air pollution, beginning with those that directly emit particulate matter, or PM 2.5. As you can see, not all states are equal contributors, and the source profiles by state also vary. California, the 8th largest economy in the world and most populous state in the country, is not surprisingly the largest polluter. Within California, the sources are relatively evenly distributed. Note that fire and dust were significant in 2008. From 2007 to 2009, California was in a drought. Overall, PM 2.5 levels were higher in 2008 than in 2006, and the drought could have been a major reason why. Dust is also a major polluter in arid states like New Mexico. All other sources is made up of agriculture, industrial processes, solvents, and miscellaneous sources. Next, let's take a look at oxygens of nitrogen, or NOx. NOx is important because along with VOCs and carbon monoxide, it's a major precursor to ozone. Ozone, while a critical element in the upper atmosphere, is a pollutant at ground level, what we usually observe as smog. As you can see, California once again dwarfs the other states, and the primary culprit is mobile sources. This is the result of a large population doing a lot of driving in a sprawling state. There's also lots of industry serving those people, and California houses the largest ports in the United States. Ships, trucks, trains, and supporting equipment, along with a vast number of passenger cars, are the reason that California's NOx levels loom large over other western states. California has done better with sulfur dioxide. As you can see here, the largest states for sulfur dioxide emissions are Arizona, Colorado, and Wyoming. What these states have in common is coal. Coal power plants are the single largest source of anthropogenic sulfur dioxide. Wyoming not only gets 95% of its power from coal plants, it's also a major supplier of coal and is home to the Powder River Basin. If you look at Washington and California, mobile sources are 1/3 or more of sulfur dioxide emissions. Washington and California are not major coal-burning states, but they are home to significant marine ports. The large freight ships that carry containers of goods between the U.S. and Asia burn bunker fuel, which is inexpensive but very dirty and has a high sulfur content. Volatile organic compounds are important because they're a precursor to ozone and PM 2.5. They're emitted in many consumer goods such as cleaning fluids, paints, and printing inks, as well as industrial sources and fuels. Because they are in pesticides, agriculture can also be a significant source in some states like Idaho. Overall, volatile organic compounds are more of a concern for indoor than outdoor air quality. EPA has found that VOCs can be 2 to 5 times higher inside households than outside. Finally, carbon monoxide emissions have declined steeply, falling on average 80% below the national standard over the last 20 years due to advancements in vehicle technology and fuels. Although California remains the largest source for carbon monoxide in the West due to the large number of cars and trucks, it remains in compliance with the EPA standards. Thanks for watching this presentation. You can download more slides and other libraries at ecowest.org. A number of leading experts on Western conservation serve as advisors to EcoWest. EcoWest is produced by California Environmental Associates. Please feel free to contact us if you have a question or want to make a suggestion.